Okay, question 1.2. We have the integral from 0 to 1 of x times the square root of x, square root of 1 minus x squared dx. So this is a product of two functions, right? It is x times the square root of 1 minus x squared. So definitely integration by parts should be one of the techniques that comes to the top of your head. You'd have to be choosing one of these functions to be your u, so you'll take the derivative of that, and the other one to be your du, so you'll dv, so you'll take the antiderivative of that. But unfortunately, if you play around with it, neither of those will really work out. Right? If you let this be your u, then you'd be replacing that with 1, so that's great. But you'd be replacing this with its antiderivative, and I don't even know what that would be. Right? You have to take the antiderivative of the square root, which would be like some kind of trig thing, maybe? It's not it. Not the move, not the move. Okay, so maybe you go the other way. Maybe you let this be your dv, and so you're replacing this with its antiderivative. And you let this be your u, so you're replacing that with its derivative. But the way that that works out, it's not really that great either, right? So you might think about integration by parts, but if you start to work them out, you'll find it's not a very fruitful direction. In fact, the fruitful direction for this problem is simply a u substitution, right? If you have a sort of more complicated component with some stuff inside, like in this case we have the square root with some stuff going on inside, it's definitely not always of course, but definitely something to consider is letting that stuff on the inside be your new variable. Because if you do that, it might just be that the du has exactly what you need to get rid of the other stuff going on. So that's what's going on here. This integral, I can see I have exactly what I need for my du. So right here is my square root of u. And then I'm going to put the x over here to match what I need for the dx. And I also need a negative 2. No problem, I can always give myself a times negative 2, as long as I also give myself a times negative 1/2, right? So this and this are overall nothing, haven't actually done anything. And then finally I just move this x over to there. Right, so I've just rewritten what I've got. Consequently, I can make the switch on my integral. This is now, I can pull the negative 1/2 out. This is now the square root of u du, right? This was the square root of u inside there, and then this here was my du. So yeah. Now notice the bounds are still in my old variable, right? It's important to keep that in mind. So our options are either to leave these bounds alone in the old variable x, and we'll just have to remember to convert back to x before we plug in the bounds. Or option 2 is to completely forget about x and then translate the bounds with us, right? So as we make the exchange, turn these x bounds into u bounds by plugging them into here and sort of making the exchange with us, and then we never have to go back to x. We can do the whole thing in u after that. Both of those are totally valid. My personal preference is the former. I like to leave things in the old bounds and just convert back in the end. So I'm going to do that. So just remember that those bounds 0 and 1 are in x, not in u. So we should be good to make the exchange here. This is u to the 1/2. So the antiderivative of u to the 1/2, well, it's u to the 3/2 times 2/3, right? That's the antiderivative of that. Don't forget the plus c. Actually, no, do forget the plus c because this is a definite integral, so whatever. So it's that. And then, like I said, these are in x, not u, so we have to convert back to x first. We can simplify that, right? That's 1/3. And then this is 1 minus x squared to the 3/2. Okay? So now we're good to go here. So we can plug in 1. So negative 1/3. So plug in 1 and plug in 0. right? So I'm going to be very slow and careful on this because it's easy to make a mistake here, especially with that negative 1/3. Right, so it's negative 1/3 times what you get when you plug in 1. Now let's do this very carefully. When we plug in 1, we get 1 minus 1 squared to the 3/2. And when we plug in 0, we have 1 minus 0 squared to the 3/2. Right? Now some of you did this so quickly that you just said, okay, plug in 0, it works out to be 0, so this whole thing is just 0. Boom, easy. Not true. Unfortunately not. You do have to be carefully plugging in both bounds even when one of them is 0 because it doesn't always turn out to be 0. Let's take a look. In fact, in this case, it's the first term that turns out to be 0. This is negative 1/3 times, well, 1 squared is 1, and then 1 minus 1 is 0. So this is just times 0 to the 3/2. 0 to the 3/2 is 0. And then 0 times anything is 0. So this first term is, in fact, 0. 0. Okay? The second term, on the other hand, negative 1/3 times, well, 0 squared is 0. 1 minus 0 is 1. And so it's actually 1 to the 3/2. Now, 1 to the anything is 1s, including 3/2, so that's just 1. And then times negative 1/3 is negative 1/3. So this is 0 minus negative 1/3. And that's positive 1/3. So there you go. In the end, the answer to this problem is positive 1/3. And that's how you get it. Okay. Now I should say, some people got negative 1/3 as the answer. A good sense check that you should do is think about how on these bounds, this thing is positive and this thing is positive, so their product is positive. So that function over those bounds is positive the entire time. So its integral should definitely be a positive number. There's no way you can get a negative number from a function that's positive over that entire interval. So yeah. So if you got negative 1/3, you should think like I probably screwed up somewhere. And no shame to it too, because it sure is easy to mess up these signs. There's a lot of negatives floating around. It's very easy to make a mistake. Okay, so there you go. That's problem 1.2. Next one.